Assalamu alaikum. Welcome to our SAP-1 6-bit computer video presentation by Team Bytebenders. I am Maisha Rahman, ID 2100212209, along with my 5 teammates SM Rohan Ahmed, ID 2100212218, Saika Fazila, ID 2100212223, Fabiha Anbar Orpa, ID 2100212226, Fattaur Rahim, ID 2100212240, and Samiha Tasnim Mouli, ID 2100212241. Together, we are excited to present our project.
Now we will explain the concept of SAP-1. The SAP-1, or Simple as Possible 1, is a simplified computer that is built using the von Neumann architecture. It is an 8-bit computer, but here we have built a 6-bit computer by making slight modification. The 6-bit computer is a computer that can process 6 bits of data per clock pulse. This is a bus-centered computer where we have 12 main modules. The modules are connected to the bus directly or indirectly. The indirectly connected modules are actually connected through other modules to the bus. Here the modules are namely the clock, the program counter, the MAR or memory address register, the address selector, the input unit, the RAM, the instruction register, the controller sequencer, the accumulator, the arithmetic logic unit, the output unit, the B register. Here we will explain the operation of this whole system or our 6-bit computer and the modules one by one.
Now, let us discuss the main parts of our SAP-1 6-bit computer. Clock pulse generator. Clock pulse generator is a circuit that produces a regular train of pulses that drives the entire system. The clock pulses are used to synchronize the operation of all different modules of the computer such as the CPU, RAM, ALU, etc. In this parent sheet of our clock pulse generator, we can see that the clock pulse generator have two modes, auto and manual. There is a SPDT switch which is used to switch between manual and auto mode. And there is also a push button which serves as a trigger for manual pulse generator. We can also see a halt input which comes from the control sequence. When the halt is 0, the clock starts working. But when the halt converts from 0 to 1, the clock stops working. There are two outputs in the clock pulse generator. They are the clock pulse output and the inverse clock pulse output. The LEDs are used to visually confirm the active state of each output signal. If we run the clock pulse generator, and we can see that the halt is in 0 and the SPDT switch is in manual mode. So we can use the push button as our trigger of manual mode. If we push the button, we can see that the state of our clock changed from inverse clock to clock, and if we push the button again, then the state of our clock pulse changed again. And we can push our button continuously and continuously change the state of our clock output. If we convert the SPDT switch from manual to auto, we can see that the clock pulse signal is changing its state automatically in the auto mode. And we can also see that the halt is in 0. Now let us see the child sheet of our clock pulse generator. In this child sheet, we can see that the clock pulse generator is made of 3 main circuits, a stable, a monostable and a bistable circuit. A stable circuit generates a continuous and automatic square wave pulse, forming the foundation of the clock's timing. Monostable circuits produce a single and precisely timed output pulse for a input trigger, enabling the precise control over our pulse duration. And a bistable circuit toggles between two stable states, and it is used for storing and maintaining the clock's current operation mode. An integrated circuit is used to connect these three circuits, ensuring the continuous and accurate operation and accurate pulse generation. Then the output signal can be found, and we know that there are two output signals then we can found from this clock pulse generation. One is called clock pulse output, another is inverse clock pulse output.
So program counter. Program counter is a 3-bit counter which can count from 000 up to 111. Program counter's job is to store and send out the memory address of the next instruction to be fetched and executed. It will increment its value after each instruction cycle. From the diagram, we can see there are 4 input lines and 3 output lines. The input lines are counter enable, counter output, clock, and reset pins. And the output pins are Q1, Q2, Q3, which goes to the bus. Now we can see the child sheet of this program counter. So in the child sheet, we can see we have used 3 JK flip-flops and one 74AC 245 IC. The clock pulse is connected with J and K pin of each JK flip-flop, and the output of the previous flip-flop is acting as clock pulse of the next flip-flop. The reset pin is connected with uh, each flip-flops, and the counter output is connected with the CE pin of 74AC 245 IC. The output is coming from the B0, B1 and B2, which are Q1, Q2 and Q3, which eventually goes to the bus.
Now we're going to know about the MAR or memory address register of our 6-bit computer. It is a register that stores the 3-bit data from the 3-bit address data from the bus. The 3-bit addresses are generated by the program counter. To take input from the bus, the MAR unit has to have clock pulse in the positive edge, and also the input of MI pin has to be positive. The MI signal comes from the controller sequencer, and whenever the clock pulse is in a positive edge and the MI is activated or 1, the input is taken from the bus into the MAR. There are 3 outputs from the MAR module. These outputs are connected to the address selector from which it is passed to the RAM. If we see the child sheet of this module, we will see there is a IC that has 4 D flip-flops, but we have used only 3 D flip-flops from here as we need only 3-bit storage. The MI and the inputs are connected through the tri-state buffer into the D flip-flop. This is so that there is no input stored or no data stored if the MI is not activated. Basically, it is to control the storage or storing of data into the MAR unit. I'm going to explain the address selector of our 6-bit computer. It is a selector module that selects the addresses from MAR and input unit. Basically, it selects either the addresses from MAR or input unit depending on which mode we have kept our system. If we kept the system in a run mode, it will select the addresses from the MAR. If we kept our system in a programming mode or prog mode, it will select the addresses from the input unit. Basically, it will select the addresses we are giving input. If we look into the child sheet of this module, we will see that it is designed such a way that it will be able to select only one addresses depending on which mode we have kept our entire system. Also, we can see that it has 7 input units and 3 output units. The outputs are connected to the RAM.
Next, we will see how we designed 8 into 6-bit RAM. 8 into 6-bit RAM means there will be 8 address locations, each storing 6-bit data. Now, RAM has a RAM out switch which will let this 6-bit data to go into the bus, and it has read or write switch which will be used either for reading the data or writing the data into the RAM. And it has 6 data switches and 3 address switches. When the computer program is on run, then these address switches will take input 3-bit data from the MAR. Now let's see how we design this RAM by going to the child sheet. So for designing this RAM, we used 2 RAM ICs and 1 buffer IC, and we have connected RO switch with the buffer IC so that the data cannot go into the bus until this RAM out switch is enabled. And we have used 3 address switches. We have connected them at the 3 address pins of the 2 RAM ICs and shorted them as it will act as one RAM of 8 into 6 bit. So we have shorted them, and we have connected 3 data switches to one RAM IC and another 3 data switches to another RAM IC. And we have taken the output from each RAM IC and connected them to this buffer IC. So this is how we designed 8 into 6-bit RAM, which will let the data go into the bus when RAM out switch is on, and which will take input from the input unit when it is on write mode, and it can read the data when it is on read mode.
Instruction register. It holds the current instruction so that it can decode and give input to the control and timing unit. Specifically, the instruction register holds the opcode which defines the type of instruction. The function of instruction register is to receive and store the 6-bit instruction placed on the bus from the RAM. The contents of the instruction register are then split into 3-bit segments. The upper 3-bit goes into the controller sequencer, while the lower 3-bit should be sent to the bus. A reset pin is required for resetting the instruction register when the computer starts. Now we will see the child sheet. Here 74HC173 IC is used, which is a deregister IC, to store and transfer the inputs. A buffer IC 74LS245 is used to prevent the lower nibble from going into the bus until I/O is enabled. Instruction register input writes the current values of the bus into the register. Instruction register output sends the stored data onto the bus. Output pins are disconnected when AO is low.
The controller sequencer is a very important part of our 6-bit computer. We can also consider it as the brain of this whole system because it controls. It controls and it creates sequences among all the modules of any operation we code it to do so. Here we can see the controller sequencer has 5 input pins and 13 output pins. Among the 5 input pins, we can see there is a reset pin through which we can reset our controller sequencer. By resetting, here we are actually resetting the states we're in inside the controller sequencer. Also, we have a clock input through which we control the controller sequencer using the clock pulse. There we have C1, C2, C3. These are the inputs which receives the signal from the instruction register. The signal we receive from the 3-bit signal we receive from the instruction register is what creates the control signal or sequential signal we are supposed to create by controller sequencer. The controller sequencer creates 13-bit 12 signal bits, which are basically the control bits, and there is a halt signal that is created to halt the function of clock. Whenever the halt signal becomes activated or becomes 1, the clock turns off. That means the entire system turns off, as there is no clock pulse being supplied to the input of the modules. Here, the CE control signal is the signal. If it is activated, the counter is the value that is available in the counter is incremented. If the CO is activated, the value that is available in the counter is sent to the bus or given output to the bus. The MI is the signal. If it is activated, the memory address register takes inputs from the bus. The RO is a signal. If it is activated, the RAM gives output to the bus. The II is a signal. If it is activated, the instruction register takes input from the bus. The IO being activated, the instruction register gives output to the controller sequencer. The AI being activated, the accumulator takes input from the bus. The AO being activated, the accumulator gives output to the bus. The SU being activated, the ALU does subtraction operation. The SH being 0, the ALU does addition operation. The EO being activated, the ALU gives output to the bus of the result available in it. The OI being activated, the output unit takes input from the bus. The PI being activated, the B register takes input from the bus. That's how the controller sequencer controls and makes sequence of all the operation.
Right now, let's understand the schematic design of accumulator. Accumulator, also called A register, should have the ability to output intermediate results after each ALU operation. So, an accumulator has its input data switches, 2 enable pins and 12 output pins. Among 12 output pins, 6 went to bus and 6 went to ALU. And among the 2 enable pins, one is accumulator in, which lets the data from the bus to store into the accumulator, and when accumulator out AO is enabled, the data stored in the accumulator go to the ALU from the accumulator. Now let's see how we design this accumulator by going into the child sheet. So to design an accumulator, we use 2 D flip-flops of 7483-173 IC and a buffer IC 7483-245, so the data cannot go into the bus until the pin AO is on. Now we have connected 6 data switches. Among them, 3 are connected to one IC and another 3 are connected to the second IC. And then the output is taken from the 2 ICs and connected to the 12 output pins. So when this AI is on, we can see that the data will store in this accumulator. And when the output pin AO is on, then the data will go into the bus. This data is basically the output which comes from ALU. And this is the data which we will send from accumulator to the ALU for the required operation which we want to do. So this is how basically an accumulator works.
Now let us discuss about ALU. ALU or Arithmetic Logic Unit is the heart of SAP-1 computer. It is responsible for performing all the mathematical and logical operations that a computer needs to carry out. ALU is capable of 6-bit addition and subtraction. In the parent sheet of our ALU, we can see that the 6-bit input number A is coming from accumulator and another 6-bit input number B is coming from B register. We can also see two input unit SU and EO coming from control sequencer. There is a clock pulse input coming directly from the clock pulse generator, which derives ALU operation synchronously. The 6-bit output is coming out from the ALU is going directly to the bus bar. There is also a output sign indication to indicate whether the output is positive or negative. Now let us see the child sheet of our ALU. From the child sheet of our ALU, we can see that the ALU is mainly made of full adders, XOR gates and a flag register which carry the output from the adders to bus bar and also indicate the sign bit of our ALU. When the SU is 0, the ALU will perform addition operation and the full adders process A and B directly to generate the sum. When the SU is 1, the ALU will perform subtraction operation. At that time, the XOR gates convert B into its 2's complement and then the adders add A and 2's complement of B together, effectively resulting the subtraction. The final output O will go to bus bar.
Now we will talk about B register. B register is used by the ALU to perform arithmetic and logical operations on the accumulator and the values stored in the B register. The B register can also be used to store the values to be written to memory or output to the display. This is a B register. Now we will understand the input and output lines. There are total 8 input lines and 6 output lines in the B register. The D0 to D5 comes from the bus. The 6 output lines um, goes to the ALU. Now we will see the child sheet of this B register. Here we can see we have used 274 AC173 IC. The clock of this two register is shorted. The BI is connected to the E1 and E2 pin of both IC. The output here are B0, B1, B2, B3, B4, B5. So how does this B register work? To add two numbers together, the CPU would load one of the numbers into the accumulator and the other number into the B register. The CPU would then execute the add instruction, which would add two numbers together and store the result in the accumulator. To subtract two numbers from each other, the CPU would load the first number into the accumulator and the second number into B register. The CPU would then execute the sub instruction, which would subtract the two numbers from each other and store the result in the accumulator. To write a value to memory, the CPU would load the value into the B register and then execute the out instruction, which would write the value to the memory address specified by the MAR. To output a value to the display, the CPU would load the value into the B register and then execute the out instruction, which would output the value to the display. So this is how a B register works with accumulator.
This is our output register for getting our output. It has 8 input pins, one of which is the clock, one is OI, which is the only control input in this register, which is controlled using the controller sequencer. There are also 6 input data pins, which is connected to the bus, and it receives the data from the accumulator. On the output side, it has 6 output pins, which is connected to the output unit. Now, if we look inside the child sheet, we designed this using 274HC173, which is D flip-flop with tri-state outputs. When the control input Y is 1 and the clock is active, this output register will receive the data from accumulator, and in the same clock pulse it will transfer the data to these output pins. Now if we come to our output unit, this has 6 input pins which is connected to the output register and 8 output pins which is connected to 2 BCD displays. This output unit is designed using double method. Now if we look inside, we have 4 subcircuits. Each of the subcircuit is designed with the same circuit diagram. This circuit is designed using double method. To get the outputs, we have used this truth table. Now how the double method works? The double method shifts each binary digit at a time, simultaneously checking for the binary number if the binary number is greater than 4 or not. If the binary number is greater than 4, then this circuit adds 3 to the number and repeatedly shifts the number until the binary number is converted to BCD representation. And that is how the double method converts binary number to BCD representation.
Running the program, first we will ensure that the clock is at manual mode. Then we will go to the input unit for inputting the data into the RAM. So let's begin simulation, and the proc or run switch should be at 1 state, and for writing the data into the RAM, read or write switch should be at 0 state. So at 000 address, we are inputting 000 100, where 000 is the opcode for loading data into the accumulator, and 100 is the address or the first number which need to be added with the second number needs to be stored. Okay, then we are writing it. Okay, then moving on to 001. 001 101. 001 is the opcode for addition. 101 is the address or the second number which will be added with the first number need to be stored. Then we are writing it. Moving on to 010. 010 011 000. 011 is the opcode for output. 000 here address need not to be specified for output. So we are giving here 000. We are writing the data. Now 011 we are inputting 111 000. 111 is the opcode for halting the program, and here again address need not to be specified. We are writing it. So finally we will input the program, input the data. So at 100 we are giving suppose 8. At 101 we are giving suppose 2. Now we will run the program. For running the program, proc switch should be at state 0. So let's take it at auto. Data is loaded. Okay. So what we added 8 and 2. So the result is 10. So the result is okay. Here delay is occurring due to the clock circuit, because in clock circuit if we change the resistor and capacitor values, then the delay can be minimized, and also there are many NOT gates and which are making the delay, I guess. So it can be changed. Now here we can see that at B register 2 is loaded, which was the second number. Then at accumulator, the main final result from ALU is going into the accumulator, that is 10. Here actually the bits are in inverse order, so we cannot understand that it is 10, but it is 10. Here 0 is the MSB, and here 0 is the LSB. Okay, so now we will move on into the subtraction operation. We will basically subtract 1 from 0. So what should be the result? -1. Then we will again start simulating the program for resetting everything. and take the clock again at manual mode. So here for inputting the data, everything will be in a similar approach, but here the opcode will be 010 at 001 address. So let's start. Proc switch should be at one state as usual. So let's do the programming. So here we are giving the opcode 010. Okay. So here we are giving the first number 0, and at 101 we will give 1 because we want to subtract 1 from 0. Okay. Then we are running the program and let's see what will be the result. It should be -1. So let's wait. Okay. So see, the result is -1. Here, similar approach, 1 is loaded into the B register, and at accumulator, we can see the result, which is -1. This result is entering from ALU, and finally, it's coming into the output register, and then it's going into the output unit, and then the result is being shown in BCD. Okay, let's now do one more operation. Suppose we want to subtract 3 from 5. So again, we will stop the program and take the clock at manual mode. And we will program in a similar approach. So let's start. Um, so we want to subtract. Acha, suppose we want to subtract 8 from 10. Here, from the result is going from accumulator. We had seen that 1010 had come. So yeah. So what we did, we subtracted 8 from 10. So the result is 2. The result is right. So after doing the addition and subtraction operations, we can see that our program is running successfully. We can do the addition and subtraction programs successfully. When we subtract larger number from smaller number, then the sign is coming minus, and when we subtract smaller number from larger number, then the sign is then the sign bit is 1 actually. So we cannot see any sign here. So we can see that our program is correct. Our team Byte vendors, collaboratively designed and successfully executed our SAP project. This achievement is the result of our combined efforts. I hope you enjoyed watching the demonstration video of our SAP project. Thank you for tuning in to this video.
At the very end of the video, I want to thank our digital electronics course teacher, Dr. Rakibul Hassan Shagor sir, Associate Professor of Department of Electrical and Electronics Engineering, lab teacher Nadim Ahmed sir, lecturer, Department of Electrical and Electronics Engineering, and our project instructor Sheikh Muntasir Mahbub sir, lecturer, Department of Electrical and Electronics Engineering. And I would like to thank all of my group mates. Thank you everyone.